Hello, in this video we will be deriving the stiffness and mass matrix of the rod element and discussing some basic things about the theory behind it. This is going to be the formula we will be using, and these are just some importing the libraries we will be using for this. Anyway, let's start by drawing our rod element. The rod element has a length of L, a cross-sectional area A, and a Young's modulus E. It has two nodes, and 2 degrees of freedom, V1 and V2. So, the first thing we need to do is to, let's say, guess a function that will describe how the displacements will vary along the road. Because we have 2 degrees of freedom, we are going to use a polynomial that has 2 coefficients. This is the linear polynomial, the simplest of all, a0 plus a1x. Now, this polynomial and every polynomial is actually nothing but a0 plus a1, the vector of the coefficients, dotted with the vector of the variables. You see, a0 times 1, a0, a1x. Now, this is trivial, we won't be using it. We won't be writing it, but this is important. We need to start coding it. So, let's define it. In fact, let's first start to defining our symbols that we will be using. X, E, A, L, and we're going to use D for density. It will be used for the mass matrix. I haven't wrote it yet in the diagram I made. Anyway, write symbols X, E, A, L, and D. So, yes, symbols. See, I write X, it types X, E, etc. Now, let's say our C here will be the vector 1, x. But this is in list format, we need to put it in matrix format, so simply I can understand it. So write matrix 1, x, and if I now type C, you get this thing now, 1, x. But I want it in its transport form. I want to write the column in a raw form, so I'll just transpose it with this command, and we have this. Now, let's say that we want to calculate these 2 coefficients. In order to do that, we need to know the values of the function at its nodes. We need to know whatever v1 and v2 is. But before that, we need the coordinates at this point, and this polynomial evaluated at its nodes, at x equals 0 and at x equals L. So, let's do that. Let's say that our C1, which will be the matrix that contains this row, this one, evaluated at 0, and its second row will be this one evaluated at L. So, if I just sub in 0 here and then sub L and add them, they will just be added in the same row, and I won't create the matrix that I want. In order to create the matrix, we're going to use Python's way of manipulating lists. So we'll just add the substitutions inside the lists. So all in all, a second list will be created that will have these lists as components. So let's sub for x equals 0. This thing here is a bit annoying, but this is the way SymPy understands substitution. And then we will sub L. And let's see now, C1. Now, so this is what has happened here. We want that. We don't want that, of course. We don't want it in this format, so we will just write here matrix, and you see now it is exactly in the format we want. This is the row with our evaluation at 0, and this is the row with our evaluation at L. So we've got this matrix which is 2 by 2, right? And this is, let's say this now is C1, okay? And we dot it with the coefficients. Let's call it A. This will need to equal the values of our function. Now, what we want to do is have at the first time the first degree of freedom be equal to 1 and the second one to be equal to 0. All in all, in vector notation, it will be 1, 0. This is the first time. Now the second time, we need this one. We need the second degree of freedom to be 1 and the first one to be 0. So this will be 0, 1. Now, C1 is 2 by 2. The result here is also 2 by 2. This means that A needs to be 2 by 2 as well. This is why we are not writing this one, because actually it will be 2 more coordinates, 2 more coefficients to create this matrix now. Now, we want to find this one. We want to find A. We got C1 and we got this. But notice this one is the identity. Whatever we multiply it with will stay the same. So what we need to do in order to calculate A is to inverse this one, is to inverse C1. If it goes this way, then A is going to be C to the negative 1, C inverse. This is very easy to write. We just write A equals C to the negative 1. Let's see what A is now. Y. Yeah, C1. So this is the inverse matrix. And now this matrix holds the coefficients of the polynomial. In order to get the polynomials, we need to multiply it with C. So this is exactly what we're going to do. C1, yes. No. Well, C is 1 by 2 and A is 2 by 2, so we need to multiply it this way, not with A from the other side. So we get that. These are the two shape functions of the rod element, and we can check it. If we plug in 0 to this one, we get 1. Exactly as we like the first degree of freedom to be 1. And if we plug in L over L equals 1, 1 negative 1, 1 minus 1 equals 0. So it's correct, and the same one applies for this one. plugging x equals 0, we get 0, plugging x equals L, L over L 1, so we get 1. So this is a bit of check, and it is correct. Now, let's talk about this formula. What is B? B is actually the strain matrix. The strain matrix is the derivative of the displacement matrix. We have assumed the displacement takes this form. So B is nothing but the derivative of this. The derivative of the shape functions. D is the material law. The material law in this simple case is just E. It is the Young's modulus. So let's call this N. N is the most common letter to describe the shape functions. And we need to differentiate it with respect to x. So B is going to be N diff x. And let's see what happens. You see B has been differentiated, N has been differentiated, and we get this matrix. So we got B, we got D, and we got B as well. So let's integrate. To integrate, we just need to type integrate B T times E, which is the material law D, times B, comma, and then the variable of integration, and then its limits 0 to L. Let's see what we get. We get this matrix right here. This is correct, but it is not yet complete, because the integration is over the volume of the element, and I only integrate with respect to its length. This means that we need to integrate now to the area of the cross-section, but the assumption for the rod element is that the cross-sectional area is not varying the function. So if I integrate with respect to the area of a constant curve, I'm going to just get the area, not the curve, but the surface. So I will just get a constant A. I've made a mistake previously and I had to restart it because I had defined A already, and I could not understand why it broke here, and I've changed them to A1 so it won't ring again. So let's see, now it is correct. And now for the mass matrix, let's define it as K. Let's say this is K. For the mass matrix, all we need to do is do exactly the same thing, but now instead of B, we'll integrate the shape functions themselves, and E is just going to be the density. And this is what we call a consistent mass matrix. There is another thing that is called looped mass matrix, but this is out of our topic. And with K and M, this tutorial is complete.